So algebra, homework number 9. Problem 5. So this is to prove the kernel of a homomorphism is a normal subgroup. So suppose we have two groups, G and G prime, and a function f from G to G prime, which is a homomorphism. And the definition of the kernel of f, this is all elements in G such that f of x is the identity in G prime. So it's like here we have G and here we have G prime. And let's say E is the identity in G and E prime is the identity in G prime. And we have this function from G to X. And we want to look at all of the elements of G that get mapped to this element E prime. So a homomorphism doesn't have to be one-to-one. There can be more than one element. But we also know that the following is true. So we proved that the identity in G is always mapped to the identity in G prime. So that f of E equals E prime. So therefore, E is always in the kernel of F. Okay. Any questions about anything? Just interrupt me at any time.
No.
So we're going to do this in 2 steps. First, we'll prove that the kernel is a subgroup, and then we'll prove that it's normal. So for a subset of a group to be a subgroup, it has to contain the identity. We just saw that it does. It has to be closed under multiplication, so that X be in the kernel of F. Let me call the kernel of Fk, so I don't have to keep writing this. And that Y be another element in K. So then if we calculate f of x times y, that's f of x times f of y, because this is a homomorphism. Right? And because x is in the kernel, f of x is the identity. And because y is in the kernel, f of y is the identity. And the identity times the identity is the identity. So therefore, whenever x and y are in K, then xy is in K. So K is closed under multiplication. So this is the first thing we need to prove for a subgroup. This is the second. And the third is that the subgroup is closed under inverses. So let X be in the kernel. Then if you take f of X inverse, we prove that f of X inverse is the inverse of f of X. But f of X is the identity. And the inverse of the identity is the identity. So X inverse is in the kernel. So this kernel K contains the inverse of each of its elements. So 1, 2, and 3 means that K is a subgroup. Okay. Any questions about that? So to show that it's normal, we have to prove that it's closed under conjugation. That means that let X be in K and let A be any element in the group. I have to show that AX A inverse is in K. But if you take f of AX A inverse, that's f of A times f of X times f of A inverse. But X is in the kernel, so f of X is the identity. So this is just f of A times f of A inverse. And f of A inverse is just f of A inverse. And an element times the identity is the identity. An element times its inverse is the identity. So AX A inverse is in K. And that's the end of the proof. The first three steps show the kernel is a subgroup. And the last step shows that it is a normal subgroup.
Mhm. Okay, got it. Can you go also over 7?
Yep.
Okay.
So homework 9, number 7, we have two homomorphisms, a homomorphism F1 from G1 to G1 prime, and a homomorphism F2 from G2 to G2 prime. So then we have to define the product groups G1 times G2 and G1 times G2 prime. That is, you have to know what these are as groups. So let me just review that. So G1 times G2, this is all elements of the form, say X1, X2, all ordered pairs, where X1 is in G1 and X2 is in G2. That's what this set is. It's the set of ordered pairs. With multiplication, defined as follows, if you have x1 comma x2 and y1 comma y2, so these are two ordered pairs in this set, you multiply them by multiplying the coordinates. And then one can check that this satisfies all of the conditions to be a group. So let's define a function f from G1 cross G2 to G1 prime cross G2 prime by f of x1 comma x2. x1 comma x2 is some element in this product equals something over here. So just apply f1 to x1. That gives you an element in G1 prime, comma f2 of x2. That's an element in G2 prime. And we want to prove f is a homomorphism. That is, we must prove that f of the product of two elements, x1, x2 times y1, y2 is f of x1, x2 times f of y1, y2. So that's what it means for F to be a homomorphism on the group G1 cross G2. And that's just a calculation that we have to do. So let's calculate, what is this? F of x1, x2 times y1, y2. When we multiply in G, this element is x1, y1, comma, x2, y2. So we're taking f of this element, which is f1 of x1, y1, comma, f2 of x2, y2, because that's how the function f was defined. But we know f1 and f2 are homomorphisms. So this is equal to f1 of x1, f1 of y1, comma, and this is f2 of x2 times f2 of y2. And this is the product of f1, x1, f2, x2 times f1, y1, comma, f2 of y2. And this element right here, this is f of x1, x2, and this is f of y1, y2. So here we have the left-hand side equal to this, which is the right-hand side. So that's the complete proof. There it is, all visible at once.
Okay, got it. Thank you.
Sure.